Welcome to this video about rotating points using Cartesian coordinates. My name is Daniel Bowers, creator of atutor.xyz. This table of contents is clickable, so to skip to any part, just click on the item in the left-hand column and it will take you directly there. There's also a table of contents in the description that you can click on, and you can click on the left and right arrows to skip around in the video. First, we're going to rotate points about the origin in multiples of 90 degrees, so 90, 180, 270, etc. Also, negative 90, negative 180, etc. In this example, we need to rotate 3, 6, 90 degrees about the origin. So the first step is to plot the point 3, 6. Instead of thinking in terms of x and y distances, let's think in terms of out and over distances. This point is out 3 and over 6. So let's rotate this 90 degrees, that's counterclockwise, and trace or hover above the paper to keep track of how far we go. We're going to go out 3 and over 6 again to find the new point. So our answer is negative 6, 3. In example 2, we need to rotate this triangle 90 degrees about the origin. The first step is to plot the points. If we have a shape, I recommend connecting them with a dotted line. I also recommend labeling them P1, P2, and P3 in this case. We use the same method to find the new points, and we label those P1 prime, P2 prime, and P3 prime. P2 is out 2 over 10, so going over 90 degrees, again we go out 2 over 10 to find P2 prime. P3 is out 4 over 2, so we do that again to find P3 prime at 4, 2 in terms of the origin, x value being 4, y value being 2. You can also do the spirals the other way, but it looks too much like a swastika for my preferences. I recommend you connect the new points with a solid line. That way you easily see the new shape and the former shape. Here is our answer. You'll notice I put my ordered pairs within set signs, the curly brackets. Make sure to keep your answer in the correct order. If you put a corresponding point in a different spot from its original point, then the answer will be wrong. In this example, we need to rotate a rectangle. So our first job is to plot the points, and I recommend connecting them with a dashed line. 180 degrees is the exact opposite. So before we started going right, now we start off going left to find P1 prime. So P1 was out 2 over 2, P1 prime is out 2 over 2. P2 is out 2 over 4, P2 prime is out 2 over 4. We do the same thing for P3 and P4, and connect our dots, and here's our answer. If you don't have graph paper right in front of you, or you just don't want to make one, or you have lots of points, this might be a better way to do it. First, you have to choose the correct set of rules, and you take the numbers and you sometimes rearrange them, sometimes find the opposite to get the new ordered set. So I've demonstrated this with arrows. A green arrow means you keep the same sign. The red arrow means you find its opposite. Since you may not use colored pencils in your homework, which is perfectly fine, you can put a negative sign next to some of the arrows to indicate that they're finding the opposite, if you like. In this example, we're rotating 2, 3, 90 degrees about the origin, so we need to use the first set of rules. We make the initial x value the new y value, and the initial y value the new x value, except it will be the opposite. And by opposite, I mean the negative version of something. Our answer is negative 3, 2. In this case, we're rotating 180 degrees, so we need to use the second set of rules. This is easy. We just find the opposites of the initial values, and that gives us the answer 3, 5. If we're rotating negative 90 degrees, that requires the last set of rules. It's the same as rotating 270 degrees counterclockwise. So we know that the new y value will be negative 6 because we need to find the opposite of the initial x value. And negative 2 just stays the same and comes to the front. Our answer is negative 2, negative 6. This is pretty much the same as rotating 90 degrees about the origin. In this example, we need to rotate a triangle about a non-origin point. So let's plot all of those points and start using the same method as we did before. Out 1 over 2, out 1 over 2. Out 1 over 8, out 1 over 8. We follow the pattern. We connect the points, and we write our answer. Again, I recommend you contain your ordered pairs within a curly bracket to show that they are a set. We're going to rotate another triangle. Remember, negative rotations are clockwise. Plot the points. Find the new P1, known as P1 prime, by going out 7 over 4. Out 10 over 8 finds P2 prime. Out 2 over 9 finds P3 prime. This gets a little bit more complicated. If you recall the arrows method, the matrices pretty much do the same thing. It's not that much harder to learn about matrices. So if you want to do something that might be more useful in the future, I would prefer this to the arrows method before. It also has the benefit of being able to do any rotation, not just right angle rotations or multiples of them. So we start off with this concept. We're multiplying two matrices together to find the new matrix, which shows the new points. And we set it up like this. The rotating matrix uses trigonometric functions of an angle. You multiply it by the original points, and you get the new points. In this example, we're going to rotate 5, negative 2, 63 degrees about the origin. So let's write our formula, which I recommend doing even if you can find it in a book. It will be useful to you later on when you look back at your paper to help you remember how you did it. You could even label them if you want as rotation matrix, etc., which would be useful if you don't understand. We fill in the angle with 63 degrees and the x and y values. And now we need to do matrix multiplication, which isn't all that bad. Let's go off to the side and do that. We multiply cosine 63 degrees by 5, and add it to negative sine 63 degrees multiplied by negative 2 to get our answer. So visually, you can imagine maybe these rectangles being formed around these things to help you remember where the answer goes. So top row times first column gives you an answer in the top row first column. Now, I'm kind of using an outline structure, you might say, like similar to what you might use outlining an English essay, where the result of A feeds up into part 1. Now, if you're not sure you could keep track of that very easily, you can always indicate where a piece of information came from. In this case, 4.05 came from A. Or you might choose to highlight important information you come up with in each train of thought by maybe making a light rectangle around it. However you choose to organize your paper is fine, as long as it's sufficient to help you understand where information came from and how you got the information. Let's find the bottom part now. So bottom row of the first matrix times the first column of the second matrix gets you the result in the bottom row first column. Since that matrix is not very presentable as an answer, let's represent it as an ordered pair. The answer is 4.05, 3.55. Of course, this is approximate. This is more complicated than the last version. It has 3 steps instead of 1. So we take our points matrix, which has all our x and y values of all our points. We recalibrate it, so now it's in terms of the axis point. This is our structure. So if your axis is x-axis, y-axis, you have to put negative x-axis, negative y-axis in the second matrix there. This is easier to visualize, so let's look at our example number 1. We're rotating the point 5, around the axis point shown. We write our formula, substitute in the values, next, we take that result and we multiply it by the rotation matrix to find the coordinates in terms of the axis point of the new rotated point. This is the structure. We write our formula, substitute in, and calculate. A shortcut is to substitute by using arrows pointing to what is substituting that item. So you could go off to the side and calculate all these things, but this is just a shortcut to do that. So we find that the rotated point is -2, -2. We take that result and we have to recalibrate it so that it's in terms of the origin, not the axis point. Here's the structure. So we have the point -2, -2, which is referring to its position relative to the axis point because it's 2 to the left and 2 down from that orange dot there. Let's write our formula, substitute in, and calculate. We now know that the point is 1, 1. However, we don't want to present it as a matrix, so let's just rewrite that as an ordered pair. Let's look at some more matrices using a spreadsheet that I created for you. This should be downloadable soon from atutor.xyz. So in this situation, we're going to put inputs in the yellow areas, here and here, and we're going to get outputs in the green areas. The yellow areas are shown by the yellow and orange dot over here. So we have the yellows indicating the original points and the orange dot indicating the axis point. So here we are rotating the point 0, -4, -24 degrees. We're rotating these points -24 degrees about this axis point. And the spreadsheet has labeled everything for you and given you notes so you understand what's going on. It does all of this automatically, obviously, and reminds you that the second part is all you need if you're rotating about the origin. Okay, so it shows you all the steps and gets you the result and plots it for you. So this is the result of taking those points and rotating them. I think it was -24 degrees. So if you were to draw lines here, you would see that that's 24 degrees in the negative direction. Now let's try something else. Let's do 31 degrees. We'll switch up some things. So I picked new starting points, a new angle of rotation, and a new axis point. It works it out all automatically and gives us these result points. It looks like our results are not all on the plot. So sometimes that happens, but you can just choose different points to find better examples if you like later. Now, if you ever have to convert from radians to degrees, I have a page that does that. You can do that here. If you're dealing with polar coordinates, you can convert from polar to Cartesian or vice versa here. And there's a couple of resources here that you can check on to have other examples that you might prefer. This is a way to check your work online. I don't think it's great if you have multiple points, but if you just have one point, it's useful. This website is also very useful for checking other homework as well. Sometimes it works, sometimes it doesn't, but it's a good tool to keep in your toolbox. So let's go to this website, type in rotation information in this structure, and then find our answer at the transformed point section. So here we go. Here I'm rotating 4-2, 36 degrees about -1-3. Now instead of writing degrees, you could also hit Alt 248 to write the degree sign, and that also works. You can go down here, it discusses the interpretation. Now here's our transformed point. That doesn't look very user-friendly, so let's hit approximate form. And it gives us a much easier to understand result. While that's going, we can go down here and check out the visual representation. We started here, we went here. Very nice. It also checks your rotation matrix. If you get a different result, you had done matrices to find the result, this can help you figure out where you went wrong.